Thanks for joining us. So this is the last of the 3 webinars, and today the talk's going to be quite different from the last time. Last time we talked about calibration, and calibration was all about achieving uniqueness under a couple of constraints, and those constraints were that parameter fields allowed model outputs to fit the calibration data set, and that parameter fields were reasonable, geologically reasonable. Today it's different. We still want those 2 constraints. We still want to model outputs to fit the data, because that way we're getting information out of that field data. But this time we still want the parameter fields to be geologically reasonable, but this time we're seeking diversity. So that's the emphasis of today's talk. Now, if we're going to be talking about uncertainty analysis, we can't go very far without talking about Bayes' equation. So the first thing I'm going to do is to derive Bayes' equation and then explain what it means. Now, Bayes' equation is easily derived. Recall from our first webinar that we wrote this little yellow equation here. And remember, I was using the letter F to denote probability distributions. So what this says is that, and we've got 2 random vectors here, y and x. So what this equation says is that the probability of having y and x, and each of these has many elements maybe, the probability of having y and x is equal to the probability of y conditioned on x times the probability of x. Now, when you think about it, that's rather obvious. It's so obvious that I'll write that equation again in blue. Now I'll reverse the roles of x and y. And now I'll divide by fy to obtain this green equation. Now there's one more equation back from webinar 1, which I'll remind you of. And we said if we've got fy, to derive the marginal probability distribution of y, that is fy, I can integrate out x. So fy equals the integral over all possibilities of x of fy conditioned on x. All right, I'll substitute the yellow equation into the denominator of the green equation, and voila, there is Bayes' equation. Okay, derived in 3 steps. Now let's, and notice, by the way, that because this denominator is the integral of what's on the top, the integral of the posterior distribution of x, that is the distribution of x conditional on y, that integrates to 1 over all values of x, as it should. Okay, what does this mean and how do we apply it? So let's just recall the context that we're working in. We got a model and it encapsulates numerically processes, which I have denoted up until now using the matrix Z, processes that operate on parameters which I've denoted as filling the vector K. Model produces outputs. For some of those outputs, I have field measurements. They're contaminated by noise, which I'm denoting using epsilon. So the equation then of our lives as modelers is H equals ZK plus epsilon. I'm writing Z as an operator here because we're going to wander into nonlinear territory today. But up until now, I've written it as just a matrix. And we'll continue to do that for a while and just modify this equation to accommodate with nonlinearities as we go. So that sets the context in which I'm working in. This sets the context in which I have to apply Bayes' equation. So there's Bayes' equation rewritten now using the terminology that we're familiar with, Fk and H. Let's get rid of the denominator. We don't really need it. So it's easier to write the conditional probability distribution of my parameters conditioned by my observations, H, is proportional to this thing here called the likelihood function times the prior probability distribution of K. So let's just explain this in a little more detail. Before I do any modeling, I've got to characterize the site. I've got to understand, I've got to express what I know in the prior distribution of parameters. And when I go into modeling, that's all I have. I don't know what's under the ground. I know what's not under the ground. I may know some of the relationships between the hydraulic properties under the ground, and I'm loosely equating parameters to hydraulic properties here. So explicitly or implicitly, I've got a prior probability distribution of parameters, Fk. Now, not any figment of geological imagination that I can conjure up on the basis of that Fk actually passes muster. Any parameter field that I conjure up in my imagination has to allow the model to fit field data. That's what this likelihood function expresses. And let's just see how it expresses it. This strictly speaking says, what's the probability distribution of my observations if I were to have perfect knowledge of my parameters? Which is another way of saying, if my model is perfect, which I'm assuming, that if I knew the parameters completely, I'd have this green curve. How are field measurements distributed about that green curve? Well, they're distributed according to a probability distribution that reflects the noise associated with those measurements. So this likelihood function at the center of this is the noise that affects any measurements we make in the field. And I'm assuming that that's the only reason for model to measurement misfit. Put those two together, multiply them by each other, and I end up with the posterior probability distribution of parameters. I start off with uncertainty, I finish with uncertainty. So there's Bayes' equation, and it makes total sense. Conceptually, it's easy. However, to apply Bayes' equation in the real world is actually a little bit hard, except if certain conditions are met. And one of those conditions is if all probability distributions are multi-Gaussian and if the model is linear. So let's just look at that. Suppose the prior probability distribution of my parameters, Fk, is multi-Gaussian. Let me also suppose that the prior mean of k is 0, just to make this equation a bit easier. So there's a multi-Gaussian probability density function governing the parameters k. At the heart of that is Ck, the prior covariance matrix of parameters. This is something we've talked about a lot over the last couple of webinars. Okay, my likelihood function. I'll assume also that measurement noise, there's C epsilon at the heart of this expression in the exponent. Let's assume that this too is multi-Gaussian, there is C epsilon, and that's my likelihood function. Multiply the two together, it can be shown fairly easily that the posterior probability density function of k, that is k conditioned on h, is also a multi-Gaussian probability distribution. It is relatively easy to show that the mean of that posterior is this top green equation, which you should recognize as the one that we derived last week for Tikhonov Bayesian inversion. The posterior uncertainty covariance matrix is this bottom green equation. Now, remember from last time this beautiful matrix identity? I can rewrite those equations for k dash and c dash k simply by applying this identity. The matrices then get rearranged, and I have two alternative equations for the posterior mean and the posterior covariance matrix. The difference between these two alternatives is in the size of the matrix, one of the differences, but a big difference, an important difference, a practical difference is in the size of the matrix that I need to invert here. In these two cases, it's number of parameters by number of parameters. In these two cases, it's number of observations by number of observations. This is a particularly nice way to express posterior covariance matrix of the parameters. There's the prior uncertainty, and that is how much the prior uncertainty is reduced through history matching. This is called the Sher complement representation of the posterior covariance matrix. Okay, so far so good. Now, let's take those two equations. Let's just show them again. I'm going to rederive these equations, and I'm going to derive them using concepts with which we are already familiar, just to show you a little bit further reinforce where they come from and how they're derived. So we start off with the equation of our life as modelers. Let me add another equation to that, a fairly obvious equation, that K equals the identity matrix times K. Let's put one of those equations on top of the other and rewrite it as a matrix equation. Nothing new there. You haven't got to go too far before we've got to invoke this splendid little equation here that we've been using so many times for propagation of variance. Let me apply that to this equation to look at the joint covariance of K and H. And there it is, just applying that equation. So K is random number because we don't know the parameters of the real world. This refers to the prior uncertainty of the Ks. We don't know them. We can only express them probabilistically in our head before we go and do any history matching. So H has to be a random number too because it's a function of K, which is another random number. So there exists a joint covariance matrix which expresses the statistical interrelatedness between them. And there it is. Now let me expand this out to write submatrices separately. And notice the off-diagonal elements are 0, which saying, all I'm saying here is that CK exists on its own, the prior covariance matrix of parameters. C epsilon exists on its own, the covariance matrix of measurement noise. Covariance matrix, well, the parameters and measurement noise have no relationship between them, so these off-diagonal elements are 0. Of course, if measurement noise isn't measurement noise, but structural noise, this wouldn't apply, but we're ignoring that horrible possibility. So now let me multiply out, and there is my, my joint covariance matrix for K, my parameters, and H, my field observations. And let me name these submatrices. This is CKK, that's just the covariance matrix for parameters. CHH, the covariance matrix of field measurements. And with the off-diagonal terms named with subscripts that express the fact that they're linking K to H. All right, let's retain those and go back to something we learned way back in webinar 1. And there we said, if we've got two random vectors, X and Y, and they're statistically interrelated, then there's correlation between them. That means I can condition one by knowing the other. If these have a multi-Gaussian distribution, if suddenly I know Y in this case, then I can work out a conditional mean for X and a conditional probability distribution for X, which has an uncertainty less than its prior or marginal. So let's just make a couple of assumptions. Let me assume that the prior means are 0, so we're just working in perturbations to make the maths a little bit easier. And now apply these equations to our framework where we're talking about K and H instead of X and Y. So just using our subscripts, I obtain my equation for the posterior conditioned mean of K. Now, if these terms here, I can get them from down here. There they are. That's the equation we're familiar with. The conditional mean of K as calculated from H, conditioned by H. Same thing if I want to work out the posterior covariance matrix of K. There's the equation, use the correct subscripts, get the matrices from down there, and there it is again, my Scher complement representation of the posterior covariance matrix of K. So there we are, we can derive those equations from first principles. Now, before we go and do something with those equations, I need to make an important point. How many parameters do we need in a groundwater model? Excuse me. Now, in the past, there used to be a bit of a rule of thumb that we only have as many parameters as what we need to, that can be estimated uniquely. But I have to reinforce what I said in previous webinar, those days are gone. If we're doing decision support modeling, our job is to quantify the uncertainties of decision critical predictions. Therefore, self-obviously, the number of parameters that we need in a model is the number of parameters required to quantify the uncertainties of decision critical predictions. Whether we can estimate those parameters or not is quite beside the point. In fact, if we can't estimate them, all the more reason for them to be in the model so that we can quantify the effect of their lack of estimability on the uncertainties of predictions that we care about. Now, the methods that we talked about today, and we talked about in the last couple of webinars, they're undaunted by the number of parameters we got to handle. So there's no reason not to imbue a model with lots of parameters. In fact, you know, the golden rule should be if you don't know the value of a parameter, let it wiggle. And that way you don't understate uncertainty. So the rule today is as many parameters as you can get away with, but provided we can give proper prior probability distributions to those parameters. Okay, let's go back now and start applying these equations. So we'll start off easy with linear, then we'll get into a different territory, non-linear, where things start to get a bit harder. So linear uncertainty analysis. There's the equation of our life, and there are the two alternative forms for the posterior covariance matrix. Now, why am I building a model? I'm building a model to make a prediction. I'm going to call that prediction S. It's a scalar, I'm calling it S. And in a linear world, I make that prediction just by multiplying parameters by their sensitivities. That's the matrix equation, S equals YTK. Our old friend, propagation of variance, we need again. So let's apply that formula to that equation. And here I have two pink equations which express the posterior uncertainty of a prediction that I'm going to make. These are just two equations which say the same thing. They differ in the arrangement of the matrices. They differ in the size of the matrix that I've got to invert. This is the Scher's complement representation, particularly instructive, prior uncertainty of a prediction, and how much the uncertainty of that prediction is reduced through history matching. So, how do I use linear analysis to quantify the uncertainty of a prediction that I care about? Well, the workflow is simple. I calibrate a model. Once I've calibrated, I calculate a Jacobian matrix based on calibrated parameters. Well, that Jacobian matrix is my Z matrix. I make a prediction with the model, calculate predictive sensitivities, that's the Y vector, calculate predictive uncertainty using those equations. Conceptually simple. Can be difficult if you've got lots of parameters, if you've got to calculate that Jacobian matrix with finite differences. But let's put that aside for the moment. So we know that linear analysis is always going to be approximate because models are not linear. However, there are some things that can tempt us to use these equations, some conveniences that are really accrued in no other way, just accrued by the fact that we are assuming a linear relationship between model outputs and parameters. And the thing to notice about these equations is nowhere in any of those equations is the value of a parameter. Nowhere is the value of a field measurement. And this just follows from the linearity assumption. So this has got repercussions. Suppose I'm pondering what sort of data I should gather next. Now, almost by definition, the best bit of data to gather is that which reduces the uncertainty of predictions that I care about the most. Now, using these equations, I do not have to know if I go out into the field and make a measurement, and then my intention is to include that in a revised calibration or history matching process, I do not have to know the value of the measurement that I'm going to make because it's not in that equation. So I can quantify the worth of that data without actually having gathered that data just through using those equations. Approximate, yes. Useful, absolutely. So linear analysis has some uses. Parameter and predictive uncertainty analysis, approximate. Data worth assessment, for reasons we've just talked about. But some other things as well. Using these equations, we can easily calculate contributions made to the uncertainty of key predictions by different parameters or groups of parameters. And this can be easier when I'm looking at things like model simplification strategies. Suppose, for example, that I replace a whole lot of processes that happen in one part of the model domain, and I just put a boundary across there and say, I'm going to replace that with a boundary. It's going to be a parameterized boundary, but a boundary nevertheless, because it's simpler than a whole lot of processes that do I really care about? Okay, what errors have I incurred by doing that? We can use linear analysis to calculate the contribution that those boundary parameters make to the uncertainty of decision-critical predictions. And if those contributions are small compared with other contributions to uncertainty, which I can calculate because my model now runs quicker, then I'm ahead. So it's okay. I can justify making that model simplification. So that's another place where linear analysis can come in handy. There are utilities available through the PEST suite, which will implement these equations and calculate things like data worth and contributions to uncertainty. Other equations are available through the PEST++ and PESTPP suites. This leaves me with a couple of problems though. How do I calculate CK and how do I calculate C epsilon? They're at the heart of all these equations. Well, actually, we've covered this a little bit and I'll just refresh your memories. Remember way back in webinar 1, we said if we're prepared to accept that perhaps the prior spatial covariance of parameters is dependent only on the distance between them, then I can very easily calculate a covariance matrix from a variogram. Utilities available through the PEST and PESTPP suites, which will do this for you. These two for the PEST suites are particularly nice because they allow that variogram to vary in space. Therefore, you can have different directions of anisotropy, different ranges of spatial correlation in different parts of the model domain. And that comes in handy when we've got a large model domain encompassing many different types of geology. So calculating CK is normally not much of a problem. What about C epsilon? Well, that's not much of a problem either. So normally, as we talked about last time, when you calibrate a model, you reduce an objective function. This is the Tikhonov objective function we talked about last time. It's got two components, that which reflects model to measurement misfit, that which reflects misfit between the parameters that I'm estimating and their preferred condition. So inherent in this equation is I'm playing goodness of fit against bumps and lumps in the parameter field, ugly parameter variability that reflects overfitting more than it does information in the data. And last week we talked about ways to prevent overfitting. So at the end of the day, I calibrate my model, I come up with a fit that I'm happy with, I balance it against the appeal of the parameter field. I've got a model to measurement misfit, I've got a measurement objective function. Now, if my weights applied to those measurements were all correct, that is, if my weights were each the inverse of the standard deviation of measurement noise, then this measurement objective function would be about n, that is the number of observations that I've got. And that's easy to understand because if on average, how do I calculate this objective function? I multiply each residual by its weight, square, sum. And if the weight applied to each residual is on average the inverse of the standard deviation of what creates that residual, then on average, each weighted residual squared will be 1, sum them up, and the measurement objective function is n. So once I've calibrated a model and I make a simplistic assumption that C epsilon is diagonal, it's easy to back calculate weights such that the objective function is equal to n. When I've done that, I've got the elements of my covariance matrix of measurement noise. There's a little utility called PWT-AGJ2 supplied with the PEST suite, which allows you to do that. So coming up with a suitable CK and a suitable C epsilon is not that much of a big deal, really. All right, that does linear analysis. Now, let's talk about nonlinear analysis. And we'll start slowly and just get a little more complicated as we go along. Let's start off by not respecting field measurements. Either we don't have any or we don't care about them. And the obvious method to use here, and I'm sure you're all familiar with it, is just Monte Carlo. So we generate realizations of our prior parameter probability distribution. These can be as complicated as you like. So here I've got realizations from a geostatistical parameter field generator. I run them all through the model. I run the model into the future, and at a particular time, I may look at the range of model outputs. This might be the time corresponding to a prediction that I'm interested in. Build up a histogram based on these model outputs. And if I have enough samples, that histogram gives me a pretty good approximation to the posterior probability distribution of the prediction. So that's easy. Conceptually, it's really easy. Where do I get these from? Well, the whole science of generating geologically realistic figments of imagination is called geostatistics, and there's plenty of software around which will do that. Probably the best known is this thing called SGEMS. This uses both multi-Gaussian and multiple point geostats options for generating realistic figments of geological imagination that we can use to parameterize a groundwater model. But let's just spend a few moments looking at the simpler case for if I've got a multi-Gaussian prior. And we often use a multi-Gaussian prior for convenience, especially when it comes to history match constrained uncertainty analysis. So suppose that I want to generate a realization of a vector K, which has a prior covariance matrix CK. Suppose that K has M elements. So I've got to generate a realization of an M-dimensional parameter field. Suppose also that M is 20,000 or something less than that. So this may characterize pilot point parameters. So this is pretty easy. The first thing I do is do singular value decomposition on CK, and I get EF E transpose. Because CK is positive definite, it's symmetrical, hence when I do singular value decomposition, that symmetry is expressed by the reuse of E twice, once for the transpose. So here's the workflow. I sample a one-dimensional standard normal distribution m times. That's easy. There's 1,000 ways to do this. And I fill up a vector J. Because each element of J is independent of every other element of J, the covariance matrix of J is just the identity matrix. I'm assuming a standard normal distribution, mean of 0, standard deviation of 1. Now I calculate K using this equation with E and F taken from up here, singular value decomposition of CK. That is a sample of K, a random sample of K. And just to show you that it has the right covariance matrix, our old friend, propagation of variance, we will apply again. So CK equals applying this equation to that equation to get the blue equation. The covariance matrix of CJ is the identity matrix. Things cross out. Yes, the covariance matrix of K calculated from J in this way is CK. So that's easy. That'll work with pilot point parameters 20,000 or less. What about if we, and utilities available from the PEST suite and the PyEmu suite will allow you to do that. What about if we've got tens of thousands or hundreds of thousands of parameters? Things are a little bit more complicated. And there are a variety of ways to do this. And again, the way I'm going to tell you about now, called sequential Gaussian simulation, relies on sampling one-dimensional Gaussian distribution. So it's not very hard. It starts off this way. We select a random point from our model domain, and I'm assuming that each one of these squares is going to be a separate parameter, maybe a couple of 100,000 of them. So I randomly go to one point, and I know the mean and the standard deviation here, it's just 1 point. I generate a sample from a 1D random normal distribution. Then I use kriging to Krig to another point in the model domain. Now, kriging, as you all know, is an interpolator. It gives us an expected value at that point, and it also gives us the uncertainty at that point. Well, if we're just doing interpolation, we want the expected value. If we're doing random field generation, we generate a random number centered on the expected value using the kriging calculated uncertainty at that point. Now I've got 2 points. I krig to a third point, same thing. And all the while I'm sampling a one-dimensional normal distribution with kriging has given me the mean and the standard deviation at that point. I simply sample that. And it goes on and on and on, randomly selecting points, using kriging to get the mean, standard deviation, generate a one-dimensional random number. And if there's points that I know, that's easily incorporated into the process. Points where, for example, I may have done a pump test, so I don't need a random sample because I already know the properties. Easy to do. So coming up with a multi-Gaussian prior is not a big deal, no matter how many points, how many parameters we have. And software like SGEMS will do that for us, and there's other public domain utility software which will do that for us. Okay, let's move on. Let's take a giant step forward and let's no longer sample the prior. Let's now start looking at how we sample the posterior. So now We've gone up one quantum level of difficulty. Now, one way to do this, which you've all heard about, is rejection sampling. I'll just talk briefly about it and then strongly suggest you never use it, but it just shows you in principle how this can be done. Then we'll look at more efficient ways. So with rejection sampling, we generate lots of samples from the prior in ways we've just been talking about, perhaps. Run them through the model, run the model over the past. Then we look at the field measurements and we say, okay, only 2 of these really allow us to fit the data. So when I run the model into the future, I'll only use those 2. And when I've got enough samples of the prior, which allow me to fit the past, I will calculate my predictive probability distribution from them. Now, it's a little bit more complicated, not much. Normally, we generate a random number to decide whether we reject or not. But in practice, we might say that if the objective function is less than a certain value, I'll accept, otherwise I'll reject. Now, simple in principle, it can be shown that it's Bayesian. In practice, fairly disgusting. The reason is because if we have any more than a few parameters, the acceptance to rejection ratio is going to be incredibly small. We might have to do 1 million model runs, wasted model runs. If it's a complex model, that can take a long time. And only a few parameter fields will slip through, not get rejected. And even then, they probably won't get rejected because we've got a fairly low threshold of acceptability. We'll say, oh, I'll accept this parameter field even if it just gives a halfway good fit with the data. Now, that's not good, because if you've gone to invested money to acquire data and you're accepting a halfway good fit with the data, there's information in that data which you're turning your back on. So for 2 reasons, this is not good. So rejection sampling, even though intuitively it's nice, in practice, it's not good. The only excuse may be if we've got categorical parameter fields that are difficult to adjust. Now, all the methods we're going to talk about from now on, we get much more efficiency than rejection sampling, not through rejecting, but through adjusting parameter fields. If we can't adjust the parameter fields, well, you could argue that, well, rejection's the only option we got. In fact, it's not. And there's a method I'll talk about at the end of this webinar where we don't have to waste model runs, even if we do have categorical parameter fields. But that's coming in a few minutes. So that's rejection sampling. Now let's look at some other methods which take the same principle but are a lot more efficient and a lot better to use in groundwater modeling context. Let me first mention a couple that I'm not going to talk about because even though they're fairly common, we don't use them in groundwater. No doubt you've heard of Markov chain Monte Carlo. This is another sampling method which does rely on throwing away some parameter realizations after testing them. But the hit to miss ratio is a heck of a lot better than for rejection sampling. However, it's not good enough. The method doesn't work well if we've got any more than a few tens of parameters, and it's very difficult in high-dimensional parameter spaces to ensure that we are covering the entirety of the prior parameter probability distribution. So even though this is used in cases where we don't have many parameters, in general, we won't be using this much, if at all, for calibration constrained groundwater history matching, for sampling the posterior probability distribution of groundwater model parameters. So I only mention it because it's fairly commonly used, but mention also that it's not really appropriate for us. Null space Monte Carlo used to be one method you could use through the PEST suite. I don't use it now, it's superseded by ensemble methods. Another method that had some currency in the petroleum reservoir modeling industry for a while was randomized maximum likelihood. Now, it's also not very efficient, but I'm going to talk about it. And I'm going to talk about it because this is going to be our way in to ensemble methods, because ensemble methods apply the same principle, but in a much more efficient way. So let's just spend a few moments talking about randomized maximum likelihood. So I start off, of course, with Bayes' equation. And I'm going to assume multi-Gaussianality. So here's my prior multi-Gaussian probability distribution. Notice that this time I'm going to retain the prior mean in the characterization of this distribution. At the center is CK, as we expect. Likelihood function, multi-Gaussian distribution, residuals, C epsilon at the center. Now, remember we said last time, if I want to calibrate my model, if I want to obtain the posterior mean parameter set and predictions which depend on it, I minimize this objective function. And you see this term here, there it is in the prior multi-Gaussian probability distribution, and this term here is in the likelihood function. And when I minimize that objective function, here's our old friend that we derived last webinar and we saw again this webinar, the posterior mean calculated through sensitivities using this matrix equation with this inversion here that has to be done to calculate the posterior mean. If I assume that the prior mean is non-zero, this equation is just slightly modified to accommodate that. Same principle though. And if my model's nonlinear, then I don't just apply that equation once, I apply it many times. So I start off by calculating an improved parameter set, recalculate the Jacobian matrix, that's the Z matrix, improve it again, recalculate the Jacobian matrix, improve it again, until there are no more changes, then I've got an estimate of my posterior parameter mean. That's model calibration. We talked about that last time. Okay, so I'm going to use the same principles now to obtain a sample of the posterior parameter set. I'm not going to look for the mean of that set now. I'm going to obtain a sample of the posterior, a random sample of the posterior. Two changes I have to make to this equation for the objective function that I'm going to minimize. The first change is I'm not going to use the prior mean here anymore. I'm going to use a random sample from the prior. So I'm going to look for a parameter field that departs minimally from that random sample of the prior. I'm going to acknowledge the existence of the fact that my measurements are contaminated by error, and I'm going to modify my observations by adding a sample of random noise. Then I've got an objective function which I minimize using exactly the same maths as I used before. So it's effectively Tikhonov regularized inversion, but I do it once to obtain one sample from the posterior. I do it another time to obtain another sample from the posterior. So sequentially, I obtain many different samples of the posterior parameter probability distribution. Now, this is hard work. It's hard work because, as we just said, this is an iterative procedure to minimize this objective function. And then it's got to be repeated again to obtain every different sequential realization of the posterior parameter set. So pictorially, I generate samples from the prior, run them through the model. Historical conditions, I contaminate them with measurement noise, adjust my parameters, and then when I look at the uncertainty of a prediction, I run all these adjusted parameter fields into the future. I don't throw away anymore. I adjust to get the posterior probability distribution of a prediction that I'm interested in. So here's the workflow, the flow chart. I minimize this objective function with a random sample of the prior here, a random noise-enhanced version of measurements here. It's an iterative procedure, so Z has to be updated every time an iteration of this minimization function happens. I use this equation, which we've seen before, and reuse it and reuse it. I then have a sample of the posterior, then I go to the outer loop, start again with another random prior, another realization of the measurements, and do it again and again. So you can, not realization of the measurements, another realization of measurement noise added to the measurements. So you can see that it's numerically intensive. It can be shown that if multi-Gaussian conditions are met, it's Bayesian. And at the end of this whole laborious process, I end up with many different realizations of the posterior parameter distribution. Now, it's quicker than rejection sampling, but it's not quick enough. So how can we improve on this? Well, we're now going to look at the iterative ensemble smoother, and it's able to improve on the efficiency of this process by about 2 orders of magnitude, and we'll show you how now. So if I'm going to use IES, the first thing I do is to generate lots of different parameter fields, samples of the prior. And I'm going to put them into this big matrix K. So each one of these vectors here is simply one of these realizations of the prior. I'm just putting them all alongside each other and calling it a big matrix K. Here's my field observations. These are all the same, of course, but I contaminate them with a different realization of measurement noise, put them into this big matrix H, stack them all alongside each other. And then I use this equation, the same equation we used before, to simultaneously improve all these parameter realizations. So I'm using a matrix here, K capital instead of lowercase k, H capital instead of lowercase h, just to show that I'm applying this equation, which we looked at and derived before, but I'm applying it to all these h's simultaneously to obtain simultaneously a whole lot of samples of the posterior. It's an iterative procedure still, but it's a parameter adjustment procedure. And the first big quantum leap in efficiency we gain is through doing all these adjustments for all these parameter fields together rather than sequentially. So that's quantum leap in efficiency number 1. The second quantum leap in efficiency comes from the fact that calculation of this Z matrix, I'm not going to devote any model runs to that. I'm not going to use finite differences or adjoints or anything like that. I'm going to calculate an approximation to Z from the parameters themselves as they are morphed from the prior to the posterior. Therefore, no model runs committed to calculating a Jacobian. It'll be an approximate Jacobian, but it'll do the job. And that gives us the second quantum leap in numerical efficiency. So let's see how we calculate Z from these realizations as they are morphed through the iterative ensemble smoother process. So there's my fundamental equation. But if I run the model once with the parameter set K, I get a set of model outputs O. Let me add to that equation, this rather obvious equation, stack them on top of each other to make a matrix equation. And now what I'm going to do is look at the covariances between parameters and model outputs. Remember, K is random, so is O. So there's a covariance between them. And I'm going to use a sneaky but obvious trick to calculate an approximation to Z from the covariance between them. And I'm just going to calculate these covariances empirically from the realizations of parameters and consequential model outputs themselves. So that is this E superscript says empirical. So I'm just going to use simple formulas that you're all familiar with to calculate empirical covariances and cross-covariance terms between parameters and model outputs. So this is the matrix that I'm after. This is just a covariance between model outputs, covariances between parameters, cross-covariances between them. Now, let me apply our old friend, propagation of variance. Let me apply it to this equation. So if I apply the propagation of covariance to this equation, I obtain an explicit equation that allows me to calculate these sub-matrices. Let me apply that equation. There it is. Now I've got the terms of these sub-matrices. So let's look at this one here. This is the cross-covariance between parameters and model outputs. Let me write that in green, making it very explicit that this is equal to this. Pre-multiply both sides of that equation by the inverse of CK, and there's my Z. So this shows you that notionally I can calculate Z from things that I can calculate empirically as I adjust parameters and calculate model outputs from them. All I have to do is obtain these and I can get that. And I'll show you in a moment how to do it, but let me first point out that I never actually have to do it. For the moment, I'm showing you how you could calculate Z if you want to. In a moment, I'll show you you don't really have to calculate Z. But first, let's just show how we could calculate Z if we want to. So there are two equations that we're already familiar with. Let me write this as matrix to acknowledge the fact that all these calculations are being done together as the ensembles as a whole are being used by the model to calculate an ensemble of outputs. There's my vector K of prior realizations, all the individual realizations just laid out alongside each other. And there's my corresponding matrix of model outputs, just corresponding vectors all laid alongside each other. First thing I do is calculate this thing called K bar. This is just an average. So the ith parameter here is just the average of all those along here. So this K bar is just repeated all through here. And calculating an average, that's something you learned to do back at primary school. I just, simple formula, calculate the average Ki through the average of all the realizations and stack them all alongside each other just to form this matrix K bar. Same with the model outputs. Easy, easy mathematics. Doesn't get any easier than that. Now, using maths, which is only slightly harder, but which you learned back at school, to calculate empirically the covariance between two random variables. We did this back at webinar 1. So to calculate the covariance between parameter I and parameter J, it's just Ki minus the average of K, Kj minus the average of Kj, sum them up, divide by the number of realizations, expressed nice and concisely using matrix notation using this equation, I can calculate an empirical covariance matrix of K just from my realizations. I can calculate an empirical cross covariance between K and O just from the realizations using very simple mathematics expressed in a very simple matrix equation. So there I have it. Without actually having to calculate my Jacobian matrix, I've calculated my Jacobian matrix, or an approximation there too. An approximation that's good enough to allow me to improve the initial realization of parameters till they become from the prior parameters to posterior parameters. Each time I do that, well, it only takes n model runs to do that, but I don't actually commit any model runs to this process because once I've got Z, I update my parameters using the equation we've now seen so many times, all together, all in parallel, not sequentially, using the same Z for all of them. And I was going to do those runs anyway because I want to see how the objective functions improved with my new parameters. And by the way, now that I have new parameters and new model outputs, I apply these really simple equations to get a new Z, do it again and again. And before I know it, I'm sampling the posterior. But it gets even better than this. Here's that equation we've been talking about, same equation we've been talking about a lot in this webinar and the previous one. Let me just ignore this term. Let's just work in terms of parameter increments rather than absolutes. Once I ignore that term, I can use this beautiful matrix identity to rewrite that top equation as the bottom equation. And here, the matrix I have to invert is now number of observations by number of observations. Now some truly beautiful things can happen. You see this ZCKZ term here? Well, let me write what happens when we operate with our model on a bunch of parameters to get a bunch of model outputs. Let's look at what happens when we do it individually. Our old friend, propagation of covariance. There, the empirical covariance of O is just Z, CK, ZT. And that can be calculated from my model outputs. So I just substitute this into here to get it here. I just put this easily calculated term in the equation here. I no longer have to calculate Z, CK, ZT. See this term here? Well, that's just, remember this from a couple of slides back? The covariance between my model outputs and my parameters, since simply that, which is that, make the substitution after easily calculating KCKO empirically using simple formulas that we've been just showing, just additions, multiplications, and a division. Put that in there, and there's the final equation. So I've updated my parameters using terms that I can calculate from the parameters themselves using the simplest of mathematics. So you can see why ensemble methods are getting so much traction. The matrix I have to invert is only the number of observations. I can have zillions of parameters here, and the inversion process gets no bigger. These matrices are all calculated just from the ensembles themselves using the simplest of calculations. The programming is easy. So in effect, okay, I've made a few simplifications here, and there are a few little tricks to make this work properly on all occasions. Strategic use of a Marquardt lambda doesn't hurt here, or applying this a little bit gradually just makes it work better. We can have problems with the fact that that Z approximation matrix is rank deficient because we've only got a finite number of samples of the parameters, and the rank deficiency incurred by a finite number of samples of the parameters doesn't quite overlap with the rank deficiency incurred by the fact that the Z matrix has a null space. remember last webinar? And that non-alignment can cause problems. But those problems can often be fixed up by doing things like localization. So there are a few little tricks here to get this to work under all conditions. But normally you can do those tricks, and normally the programming isn't hard and the efficiency is incredible. So once we've got our samples of the posterior, we run it into the future and calculate the uncertainty of our prediction. Okay, nearly finished. But before we finish, I just want to talk about something completely different: data space inversion. Now, this method's been used a little bit in petroleum, and I think it's got enormous potential in our industry. In all the methods we've been talking about so far, implied in their use is the fact that if we're going to quantify and reduce the uncertainties of the prediction, we've got to quantify and reduce the uncertainties of parameters. With linear methods, that's done notionally, but we've still got to calculate a big Jacobian matrix. And if it's finite differences, we need as many model runs as we got parameters. If we're using ensemble methods, we've still got to adjust complex parameter fields. And if they're not multi-Gaussian, that mightn't always come up with the sort of parameter fields that we want in the end. And the fit mightn't be that great, and we mightn't be assured that we've covered all bets as far as the true uncertainty of a prediction is concerned. Nothing is perfect. Everything's got good things and bad things. So, and also these are everything, even ensemble methods, they're a little bit numerically intensive. Is there a way to bypass adjusting parameters? Well, the answer is that there is a way to do this, actually. But another thing I should point out is the fact that we notionally, at least, or actually have to adjust parameters to quantify and reduce the uncertainty of a prediction means that model outputs have to be continuous with respect to parameters. Now, the real world's not quite like that. We make the assumption, we get away with it most times. But what if we want to look at cases where parameter fields are complex and categorical, and we're not even sure of the prior probability distribution, and we want to throw a few different parameter fields based on a few different prior probability distributions in here? Now, he said, well, rejection sampling will do that, but yuck. Too many model runs wasted, too little use of the information in the data that we've invested so much to gather. There has to be a better way where we can do model runs based on the prior and not waste so many of them. Well, there is a better way. So here's how it works. We don't have to adjust the parameters. We go straight from the field data to the prediction. So we generate random samples of the prior, run the model over the past, run the model into the future. And at this stage, we've got enough information to look at the prior probability distribution of that prediction, because we don't know conditioning yet. Now, let's recognize the fact that we've got some field data. Let's look at the model-generated counterparts to that field data in blue. Now, let's throw away the model, throw away the data just for the moment. So what we're going to do here is a kind of machine learning, but a very, very clever model-informed machine learning. So I contaminate these data with a measurement noise, because there is noise associated with the data. And just so I've done 500 model runs or something, I can now build up an empirical covariance matrix between the past and the future. So I can come up with an empirical covariance matrix between model outputs in the past and one or a number of predictions that I care about. And based on those realizations, looking at model outputs and the prediction alone, I can fill these terms of this matrix just empirically, the way we've been talking about up to now with ensemble methods. I can fill this matrix by the simplest of calculations. Now, once I've done that, I'll bring the data back on board. This then is the conditioning data. This is the realization of observations generated by reality, which I don't know. But I can use this to condition my predictions, of which so far I've only got the prior uncertainty. So I can say, what is the expected value of the posterior? What is the uncertainty associated with that value? Remember, it's all about conditioning. Remember back in webinar 1, we've got 2 random variables which have statistical interrelatedness between them. I've got a covariance matrix that links them. Now I know H. I can generate the posterior mean of S and the posterior standard deviation of S. There's the equation. We've seen it so many times before. Prior expected value of the prediction, posterior. Prior uncertainty of the prediction, posterior. So just through application of those simple equations and without rejecting any model runs, I have allowed my field measurements to inform the prediction with an incredibly small runtime burden. This can be done using a couple of programs available with the PEST suite, and I'm working on more as we speak. So that then, I've gone a little bit over time, that, ladies and gentlemen, brings us to the end of the 3 webinars. Thank you very much for your attention. Thank you for putting up with these long, boring lectures. If there's any questions that anyone has, now's the time to ask them. So I'm just going to stop sharing. Has anyone got any questions? There was silence, but here's a question. Here's a good question from Professor Dorothy Dix. Now, Dorothy says, thank you for the wonderful talk, John. Thank you, Dorothy. I have a question. Are there any other methods of predictive uncertainty analysis that don't force us to commit to a prior parameter probability distribution that we don't really know? Now, what an excellent question, Dorothy. So the answer is yes. One thing that I'm certainly interested in, I know Jeremy White is interested in, is direct predictive hypothesis testing. So why are we building a model? We're building a model to help someone make a decision. How do you make a decision? Well, you make a decision when you want to manage the environment so that things don't go wrong, so that bad things don't happen. So with direct predictive hypothesis testing, we say, can I calibrate a model just using the methods we've been talking about so that I fit the past and that I can also fit an unwanted future? And if I can fit them both, and if the parameter field that arises through that process, if it doesn't make me, if it's not unrealistic, according to what may be fairly subjective metrics, then I cannot reject the hypothesis that the worst will happen. And in doing so, I've found out how the worst may happen. And I haven't committed myself to a prior and possibly restricted the range of possibilities through a commitment to that prior. So I think direct predictive hypothesis testing may have a big future in our industry. Thank you, Dorothy. Eduardo says, how do localization matrices fit into the IES equations? Eduardo, I'd have to put up the equation to show it. It's a fairly simple multiplication. where you've got this so-called localization matrix. And normally the idea is that that if your parameter is a long way from an observation and you say, well, probably the sensitivity of one to the other is fairly small, you build up a big matrix and then just multiply it one for one on the matrices that are appearing in the equations that I just showed you. But there's plenty of papers that explain that. It's a fairly easy process. Jonathan, do you have a rule of thumb for weights? The weights are a very subjective thing. So what I normally, well, firstly, there's a fundamental rule. If you don't trust something, you don't give it a higher weight. But things get more subtle than that. Normally, I divide my observations into different groups, and on the basis that they're different data types or that the information that they carry pertains to different parameters. And I normally try to ensure that each observation group at the start of the inversion process contributes about the same to the objective function. That way, I'm assured, or at least I try to be assured, that the information that they contain is heard by PEST and it gets to adjust the parameters that it needs to. Now that's heuristic, and in some ways, some people say that's not what weights are about. Weights is all about measurement noise. To which I would reply, well, if measurement noise is the only thing that causes model to measurement misfit, we're in good territory, but we're never going to be there because it's never just measurement noise. And it can be shown by using various schemes to kind of equalize weights in those common sense ways. We are actually forming a very primitive device that can take account of the fact that C epsilon is not measurement noise. It's a very complicated structural noise term, and we can use that process to make sure that information that would otherwise be neglected can flow to those parameters. But we could talk for a whole lecture on weights, and perhaps we should, but not today. Justin, how much of a limitation to iterative ensemble smoother is localization? Well, I feel a bit self-conscious answering that question because I do not have nearly the same expertise on that matter as does Jeremy White, who's probably listening. So I think Jeremy would say not much. And that's because there's a few different ways of doing it. Now, yeah, of course, you could run into traps if you say that this parameter doesn't have much of an effect on this observation, and it really doesn't. But there are ways in the ensemble smoother process to you can also just detect as the process progresses whether if just from the ensembles and the model outputs themselves, what model outputs are more sensitive to what parameters. So apart from the wisdom that we can apply to this process, there are also automatic methods that work very well. Now, I guess the bottom line is, does it work? Mostly it does. Mostly you get a pretty good fit, and mostly the parameter fields, they look fine. Now, it's all based on a multi-Gaussian assumption, which is hopelessly violated. Does the parameter fields that we get out of this process completely lacking in bias and still obey multi-Gaussian distributions? Probably not. Maybe our localization strategy has a bit to do with that, but these are fairly small, I think, compared with the fact that we've been able to do amazing things to quantify at least most of uncertainty at a cost that would make any other method impossible. So nothing's perfect. There are ways that allow us to do pretty good things. You just got to acknowledge, always be on the lookout for where things could be going wrong, but often they won't. Okay, do you see DSI replacing IES in the near or distant future? No, there'll be two different things. The thing about I think in some cases, and I already have, I'd use DSI, but it's a little bit frustrating because you don't get to see the parameter field. And I think we as humans tend to want to see, you know, if a bad thing's going to happen, we tend to want to know why. And DSI is not going to tell us that. So that's the bad thing. The good thing is the incredible efficiency. It's got some problems too. You just got to look out for certain things and make sure it works properly. So I'm not going to tell you it works perfectly every time either. Always be on the lookout for where it's not working. There'll be times if you've got a big, horrible model, it takes a long time to run, where DSI certainly is something you can do so easily, and you can do it. You know, you've done your first model run for your first iteration for IES. You can use those same outputs of that same 0 iteration to do DSI. So it's a bit of a check on IES to make sure that they're giving pretty much the same answer. And if they're not, you can ask why not and ask which is doing the better job. There'll be cases where the model's just too big and ugly to run, or you want to have prior parameter fields that include different structures. For example, if I've got a fault here or a fault here or a fault here, and that's not adjustable. So DSI allows you to incorporate the unadjustable into the posterior analysis process. So I don't see one as ever replacing the other at all, but I see them as being complementary on many occasions. Matt, perhaps acting as a devil's advocate, but could you consider the inclusion of your expert judgment in the model objective function via Tikhonov regularization as baking your preconceived bias into the mean prediction and predictive uncertainty? How do you address preconceived system bias? Oh, man. Matt, I can't disagree with that. We've got to make a lot of subjective choices, not just in the parameterization, but certainly, as you point out, in the assignment of the prior. And I would say that one thing we do too little of is allow our field measurements to challenge that prior. And, you know, we'd rather put up with a less than good fit with the data than go and revise our prior or go and revise the structure of the model. There's bias here everywhere. And I think as scientists, challenging our own conceptions, I mean, that's tenet number one of the scientific method. So, you know, you're being the devil's advocate, Matt, but I think we need more devils. Yes, that danger's ever present. And so how do we avoid it? You know, do we make our prior purposefully larger on account of we may be over restricting it? Or do methods like direct predictive hypothesis testing, where we have to make less assumptions about the prior, I like that idea, because I decide after the fact, not before the fact, whether a prior is acceptable. I think challenge that prior is fundamental to what we do, and I think that's a good question to which, as always, there's no one answer. Giovanni, I used to run MCS sampling realizations using the covariance matrix and parameters obtained from calibration by assuming linearity around the best fixed values. Can this be considered a semi-linear method to adjust predictive uncertainty analysis? Yeah, I've done that too, and I've done that sometimes with great big ugly models that I couldn't do. I couldn't really adjust the parameters, and I couldn't do rejection sampling with. So as always, that's not perfect. You mightn't. So the big question there is, am I understating or am I overstating the uncertainty of a prediction? I'd suggest in most cases you're probably overstating it, in which case better to overstate than understate. So I don't think that's the worst thing to do in the world. If you can adjust those priors so that they're, you know, a linearized prior, so that it's in a might. If you put the samples of linearized prior and give that as the 0th iteration to IES may just one iteration make them fit the data better. But no, I don't see, you know, like everything, it's approximate, it's got its good things, it's got its bad things. I'm not going to say you should never do that. That sounds fine under certain circumstances to me, as long as you know the benefits and drawbacks of what you're doing. And if you reckon you're overstating uncertainty, and if the uncertainty that you quantify is overstated but still allows you to reject a hypothesis that things are going to go wrong when you manage an area, well, you've rejected the hypothesis. It's fine. Okay, amazing presentation, John. Thank you very much. We appreciate your knowledge and time. Question: how far field does parameter uncertainty influence the forecast uncertainty of a particular media? And how can use of these methods understand it? Now, I'm not sure I understand that question. How far field does parameter uncertainty affect the forecast uncertainty of a particular media? How can you use these methods to understand it? Look, I hope I got this question right, but if are you asking whether you understand the prior uncertainty of that medium, of that media's hydraulic properties correctly? And if you are, that's a damn good question. One thing we should always be checking is whether there is a conflict between our prior and our posterior. So, for example, if you do posterior parameter uncertainty or posterior predictive uncertainty analysis, and the uncertainty bounds of the posterior lie outside that of the prior, man, that's screaming at you that your prior's not right. And that one, you're referring back to the previous question, that may be a case to go back and change something about the structure of your model or about the prior. So look, every doubt you have about whether you're doing the right thing, entertain that doubt. You know, that's the mark of a scientist. Accept nothing, question everything. And if you suspect, you know, where there's smoke, you know, my experience is there's probably fire. So question everything, but also accept in the end that whatever we do in the end is going to be approximate. Hopefully we take whatever steps we need to err on the side of caution rather than understating predictive uncertainty. Okay. So that is the end of our questions, and thank you very much, everyone, for listening to this. This presentation and the webinar will be up on the GMDSI website shortly, and thank you very much for spending over 3 hours with me talking about what I think is a really important topics. So thanks very much, everyone. See you later.